we have method 1, method 2. Method 1 is the method in which you create a single complex fraction and then invert and multiply. Okay, so this is what we're going to try here. If that's the case, if that's your strategy, what you're going to do is group just or looking just at the fractions in the numerator of the complex fraction. And again, notice I turn everything into a fraction form, the rational form, so you can identify what you're working with. And we're just going to rewrite this as a single fraction. So looking for the LCDs, we know we need a denominator of 1, so I don't need to write anything, an x, and an x squared. Well, we already have one of them, so we need one more to give a total of 2. So our LCD for the numerator, for these three fractions in the numerator, is x squared. So what we're going to do is we're going to take our first fraction's numerator multiplied by whatever LCD factor is missing from its denominator. It's missing the entire thing. Minus the next fraction's numerator times what LCD factor is missing from this denominator. It's missing one of the x's. It has one. It's missing one. And then minus the next fraction's numerator, 24, times the LCD factor missing from its denominator. It's not missing anything. Okay, so you wind up with your expression x squared minus 5x minus 24 over x squared. Okay. So we've converted our numerator into a single fraction. We're going to do the same thing with our denominator. Let's convert this into a single fraction. Again, I'm going to think of everything in terms of its rational form. And I'm going to combine this into one single fraction. So I need an LCD factor of x squared based on the first fraction, x, which is embedded in the x squared, and 1, which I don't need to write. So once again, my LCD is x squared. So if I come back here, I can take my first fraction's numerator, 15, times the LCD factors missing from its denominator. It's not missing anything, so I have a plus 15. Now, actually, I'll write it normal. Okay, so we have 15 plus the next fraction's numerator, 8, times the missing LCD factor from its denominator. It's missing an x. And then plus 1, our last fraction's numerator, times the missing LCD factor from its denominator. It's missing the whole thing, x squared. So if I reorder these terms, I get x squared plus 8x plus 15 all over x squared. So what I've really done is I've created this fraction as a single fraction divided by another single fraction. I just rewritten the form of this complex fraction, and so now what I can do to solve is invert and multiply. So as I go through that process, I'm going to factor my numerator up here. So x squared minus 5x minus 24 are going to have binomial factors with the first term x. The second terms are going to be two numbers whose product is negative 24 and whose sum is negative 5, so that is negative 8, positive 3, all over x squared. And then instead of dividing by this fraction, I'm going to multiply by the reciprocal. So the x squared gets moved up, and I am going to put the factored form of this expression in the denominator. So once again, we have a leading coefficient of 1, so we're going to have binomial factors of x. The second terms of each of those factors will be the two numbers whose product is positive 15 and whose sum is positive 8. So plus 5 and plus 3. So now as I go through to simplify this, I can cancel. My x plus 3's cancel, my x squareds cancel, and so I'm left with my answer, x minus 8 over x plus 5. And as I look in the expressions that I canceled, I see that x can't be a negative 3 and x can't be a 0, so I can restrict those domains. It's true x can't be a negative 5, but that's already illustrated in the simplified form. Okay, now, the one extra thing that you need to look at, anytime you invert and multiply, you have to account for every factor in this expression that you're inverting. So whether it's in the numerator or denominator, so here all three of these factors have to have domain restrictions. Now, it turns out that they're all canceled out here, but that's not always going to be the case. So when you invert and multiply, you have to restrict the domain of every single factor, whether it's in the numerator or the denominator, of the fraction that you invert and multiply. Right? So the advantage to doing this is you get to see these canceled factors. It's a little bit easier to identify the restricted domain. The disadvantage, it's a little bit longer process than the second method, okay, which is what I'm going to go through here. Okay, so if I use this second method, the LCD method. And what we're going to do is we're going to treat this entire fraction as a whole, and we're going to multiply it by the LCD of every single fraction involved in the problem, top and bottom. Okay, so we need a factor of 1, a factor of x, a factor of x squared, so I need one more to get a total of 2, a factor of x squared embedded already, x embedded already, 1 we don't need. So here's our LCD. Now, if I was looking at this problem, because there's only one LCD factor, this method is probably a quicker, more efficient way to approach it. Okay, so what I'm going to do is I'm now going to work just in my numerator. So working just in the numerator here, I'm going to distribute my LCD through. So here I get 1 times x squared. Here this x cancels with one of these x, so I'm left with a negative 5x. And here the x squareds cancel completely, so I'm left with a negative 24. So I've converted out of this rational form into a single expression. I'm then going to do the same thing with my expressions in the denominator. I'm going to distribute through my LCD. And when I do, the x squareds cancel, leaving a 15. So again, I'm going to write that as my last term. Here, one of the x's cancels, leaving an 8x. And when I distribute here, there's nothing that cancels, so I get a 1x squared. Okay, so I've converted out of this rational form into a single expression, which I can now simplify. So I'm going to factor everything. So x minus 8, x plus 3, factor the denominator, x plus 5, x plus 3, cancel common factors, and I get my answer, x minus 8 over x plus 5. Okay, now, I happen to see in this that x can't be a negative 3. Okay, but here's the disadvantage to this method. So advantage, it's quicker. Disadvantage, you don't get to see the domain restrictions. So if you use this method, you need to go back in and identify all the domain restrictions of each individual fraction. So x can't be 0, 0, 0, 0. It doesn't apply to those two. So do I know that x can't be 0 based on my simplified form? And I haven't restricted it already, so I do need to include that. So either of these methods works. It doesn't matter which one you choose, whatever one you're most familiar or comfortable using. Approach it. All right, the first way that you can look at this problem is to solve it as a complex fraction. And that's in looking at what you guys were working on. I think everybody did it this way. Okay, so if you're solving this as a complex fraction, you could use method 1 or 2. And let's say we use the second method. Okay, so if we use the second method, what we're going to do is treat this entire thing as a single fraction. Now remember, notice I put everything in fraction form, again to emphasize what gets multiplied by what. And we're going to multiply this whole thing by the LCD of every fraction involved. So a 1, which we don't need, a root x plus 4, and a 1. So this is our LCD right here. So we're going to multiply that over itself. And now if we work just in our numerator and distribute this through, what is root x plus 4 times root x plus 4? X plus 4. And then when we distribute here, the root x plus 4's cancel, leaving just a minus 2x. Okay, so there's our numerator. We simplify. And then our denominator, okay, when we multiply here, there's no fractions being multiplied, right? This isn't in the denominator of its own fraction, just of the whole complex fraction. So really we get x plus 4 times the square root of x plus 4. Okay, so when you simplify this, we can combine our like terms. X minus a 2x nets you a negative x plus 4 over this same denominator. And if we tried to factor out a negative just to see, do these factors cancel? We get x minus 4 over, and so nothing cancels. So this is one acceptable form. Okay, one of the other things that you're probably going to see and be expected to work with is, since you look at these two bases, both of these numbers have the same base. It's the binomial x plus 4. So usually you don't want to mix radicals. You want to just leave your answers with rational powers. So if we thought of the rational power form for square root, this is going to be a 1/2. So what is x plus 4 to the first times x plus 4 to the 1/2? What do you do with powers when you multiply their exponents? You add the powers, so this is 1 or 2/2 plus 1/2 is 3/2, and you get your solution. Okay, as you do this, you do need to test, since you need to look to see, are all the domain restrictions identified? So there, and then of the whole fraction, this whole entire thing. So the only thing x can't be, it's restricted by the sign, has to be greater than or -4, can't be equal to -4 itself. And so that's all shown in the simplified form as it is.
The regular x plus 4 and the other x plus 4 in the denominator and leave it -1 root x plus 4.
Wait, you mean down here?
Yeah, because you can factor out the negative on the numerator and you cancel the 2x plus
Right, but
4.
when you factor it out, it becomes an x minus 4. So now the sign's different here. Julie? No, you could leave it either. This right here is an acceptable numerator in both these forms. All right, let's talk about the next method. Okay, the next method is a method that is, again, in my opinion, it's an easier process, but it's harder to understand, like, how to use it. But so if you can use it this way, it winds up being far less work. Right? And that is by using factoring. Okay, so if you choose to solve these by factoring, what you're going to do is you're going to rewrite everything as a rational power. So here we would get x plus 4 to the what power? 1/2 minus 2x times x plus 4. Now what power is going to move a square root or identify a square root that's in the denominator? -1/2, good. Okay, and that's all over x plus 4. So if you think of this in its rational power form, what you can now do is you can treat it as a factoring problem. You have two groups of factors separated by a minus. There's a common base between them. The base is x plus 4. And so you remove that common base. Anytime you factor out or remove a common factor, you always take out the smallest power. The smallest power is furthest to the left on a number line. So which one is further to the left, 1/2 or -1/2? Okay, so there's our common factor. Okay, as with all factoring, once we remove our common factors, whatever's left inside has to have the exact same form as the original. One group minus another group. Okay, so let's see what is left. Okay, factoring out is dividing, and when you divide exponents, what do you do with their powers? Subtract. So we're going to subtract a power of -1/2, which is equivalent to adding the opposite. And so what's left in this first group? X plus 4 to the what power? 1/2 plus 1/2, which is 1. Okay, so it's just the x plus 4. And then in the second group, we remove a power of -1/2, which is equivalent to adding the opposite. And so here, -1/2 plus 1/2 gets you a 0, so that entire factor is removed, and we're left with just the 2x. Okay? The x plus 4 stays in our denominator here. Okay, and so the final things to simplify this, any negative powers we can just move into the denominator. It becomes x plus 4 to the positive 1/2. And we can combine our like terms here. So an x and a minus 2x nets you -x plus 4. Over in the denominator, we have a common base. So we can, when we multiply exponents with the same base, we add their powers. So x plus 4 to the first, or the equivalent 2/2. 1/2 plus 2/2 gives us our 3/2. And so we get our answer. And once again, we could write it in either form. You could take out your negative, hoping to cancel a factor if possible, and finding out that you can't here. Either way, you get your correct answer. Right? So in all the problems at the end of section 4.4, there's going to be a whole bunch of them. Some of them are even start as these rational powers and negative powers. If you're more comfortable working with the first method, or this complex fraction, just convert from rational power into fraction form. And then you can solve it this way. If you understand the factoring and can do that, just use this method. All right? Okay, you guys have until 1:40 to work, so that's about 20 minutes or so. Okay, and I'll be around to answer any questions that you might have.